Hey students, last time we talked at length about our nice looking friend SASM, and we saw the Hey World message from Tech Instance. And we implemented that program with ease and no problems in understanding that concept, right? But you would be surprised to know that the compiler generated assembly implementation of programs are completely different. So the first part of this video will look into the postmortem of our Hey World program, and the second part would discuss the way a compiler implements our programs in x86 assembly. Okay. And finally, the video implements a program that takes inputs from the user and displays the results. The implementation of getting inputs from the user would be implemented in line with how a compiler would implement things in assembly, because that is more efficient, and by doing so we have complete control over the stack, which is a part of memory that is used for procedure calls. So if you want to learn why is the compiler generated assembly more efficient and how do we have more control over the stack, stay tuned to Tech Instance. Tech Instance has more for you at store, so I encourage you all to subscribe this channel and don't forget to hit the bell icon to receive important notifications. And if you have any questions, feel free to comment in the comment section. This is what we had from our last video where we implemented our Hey World program. Now to do the postmortem of this program, we need to recall the stack memory that we saw in our crash course on assembly. So this is our stack memory that is implemented inside the main memory or the RAM, right? These are the addresses that goes from lower in the bottom to higher on the top. And shortly we will see why the order is important. So our stack consists of two parts. The topmost is the part in memory used for parameters that are passed to the functions, and the lower part of the stack memory is used for save registers and local variables of the function. So the stack holds two types of structures, the parameters and the local variables of the function. Okay. Just keep in mind that this is our red line, right? Above which we have our parameters to the function that are accessed using the base pointer EBP by adding a positive offset of 4 to it. That is 4-byte alignment. And below the red line, we have the local variables that are accessed mostly using the stack pointer ESP. That is our top of the stack. So things that we need to remember as of the x86 conventions, location at the offset of 4 from the EBP is used for the return address. That is the memory location from where the program starts after returning back from the function. Or we can simply say that the return address is the saved instruction pointer. Okay. Then we have the actual parameters at 4-byte offset apart. The parameters start from offset 8, 12, 16, and so on. And the bottom part below the red line, as we said, is used for save registers and all the local variables of the function. So that at location 0, we have the old EBP, that is the stack frame of the previous function. And we will see this in detail, don't worry. We have only scratched the surface yet. Then another callee save register is the EBX that is stored at an offset of -4 from the EBP, not shown in this figure. And then we have space for all the local variables. Let's look into how this code changes the content in the stack memory as it executes. This would give us a better understanding of how a stack actually works. The first instruction here, as we know, is used for correct debugging. So we would ignore the first instruction because that is not part of our actual program. Then we had these two instructions that are used to set up the stack for our main function, also called the Prologue. And we have the finish of stack or epilogue. So we can see clearly that the EBP and ESP are the special purpose registers that are used to implement the stack in memory. Okay, the prologue and epilogue are not part of the assembly language itself. They represent a convention used by the assembly language programmers and compilers of many high-level languages as well. And this is the main body of our program that calls printf to print the Hey World message on the screen. Let's see briefly what is meant by the prologue and epilogue. The function Prologue is the setup part of the stack, and usually it does the following actions. If the architecture has a base pointer, also known as the frame pointer, and a stack pointer, also known as the top of the stack. So in the first step, it pushes the current base pointer onto the stack, so it can be restored later. Then it assigns the value of base pointer to the stack pointer so that the base pointer and the stack pointer are pointing towards the same location in memory. The stack pointer can now be moved by decreasing or increasing its value depending on whether the stack grows down or up. In x86 architecture, the stack is decreased on push and increased on pop. So just don't be confused, because the stack grows downwards when you push a value onto it, and hence needs to be decreased, and grows upwards when you pop, and hence needs to be incremented. Okay. Then we have the function epilogue. Function epilogue actually reverses the actions of the Prologue function and returns control to the calling function. It usually does the following actions, and note that this procedure may differ from one architecture to another. In the first step, it brings the stack pointer to the current base pointer. So the stack is freed from the bytes reserved in the Prologue for local variables. Okay. In the final step, you need to pop the EBP of the stack. So it is restored to its value before the Prologue. That is the address of the previous frame pointer. And the stack is increased by the pop operation. And now the stack is pointing towards return address. And we return. Easy enough, right? So essentially, epilogue reverses the effects of what Prologue initiates. Okay, let us see this in action. This is what we had, and now we look into how this code actually works. Let's look into how this code changes the content in the stack memory as it executes. This would give us a better understanding of how a stack actually works. So this is our register file that is inside of the processor, and it is connected to the arithmetic logic unit, right? These are basically a fast storage used by the processor for its intermediate computations. And it includes the two special purpose registers that are used to implement the stack. And that is the focus of this tutorials. Okay, so let's start stepwise and understand this program that we implemented in our last video. So the first two instructions that we have are the Prologue function, or the setup of the stack for the main function to track its stack frame. The first instruction pushes the EBP register onto the stack memory so that it serves as the base pointer, as its name implies, and also so that we can move our stack pointer ESP relative to EBP without being lost. Okay, so the next instruction basically assigns EBP the value of ESP, our stack pointer. So now essentially both the registers EBP and ESP are pointing towards the same location in memory. Okay, now when we push our message onto the stack, we are actually pushing the address of the first byte of the vector of bytes, that is our string or the label message, MSG. It is important that you realize that the assembler is a translation program. It will keep track of the memory locations that it uses to store the translated constants and or program variables in data segment of the memory. That is, the assembler knows the exact memory location that the next translated item will go in the data segment. For example, when the assembler finds a label such as MSG, the assembler will equate the label to a memory location where it will jump to when required. Okay. And when we call the printf function, what it does is that it executes and prints the vector byte by byte from the first byte, the one we have passed it. So it will read the string byte by byte until a signal character that tells it to stop, and that is the character 0. Okay. And now we need to finish off the stack to clear off this memory so that it can be used by the operating system for other functions or programs. So we need to move the ESP to the location pointed to by the EBP. So this brings us to the location of the old EBP, and we can now pop off the EBP to restore the old EBP of the previous stack frame. And notice that the ESP is now pointing towards the return address. Recall that when we pop off anything, we are also incrementing the stack by an offset of 4, which lands us right on the return address. And now we are ready to return. So this was the epilogue where we released the stack to free space that we have occupied for our parameters and local variables, which we requested from the operating system. And eventually we return, which simply pops off the return address, that is the saved program pointer, to resume from where we left. But just note that when I say that we have cleared the stack or released the stack, that doesn't mean we have deleted the data in those locations. The data still exists in that place. However, this data is not reliable anymore and can be safely overwritten by other programs. So now we understand one of the most important concepts of using the stack memory. And soon I am planning to record a video lecture on the address space allocated to a program by the operating system. And that includes stack memory as well. So now let's go back to SASM to continue working with our series of programs in x86 assembly. So this brings us to the second part of this video, that is to look into how a compiler would implement the Hey World code. Let us open our previous program, the Hello World. So this was our program, right? And just let me first increase the font. So go to setting, and you have the option of fonts here. So I would select the Comic Sans MS font format, and I would select 14 as the size of the font. I hope you can now look better. Okay, so this was the program that we had last time, and these were the two instructions that we used in the main body. Just remember that when we declare a string in the data section by a label, for example, here we have MSG, that essentially gives us the address of the first byte in memory location, which is mapped to this label MSG, right? And what we do is that we need to push this message onto our stack. So we use the push instruction to push the memory address of the first byte of our string. And when we display that message using the printf to display the results, right? So this was our message. Tech instance says Hey World with a \0 that tells the assembler the end of the string. And if you run this program, once again, let's just see, you can see that the message is printed in the output doc, right? So we need to push this message onto our stack, which essentially gives us the address of the first byte in memory location, which is mapped to this label MSG, right? And then we use the printf function that displays the message in the output doc, okay? And we also know that push and pop are basically used to write and read from the stack, respectively. However, push and pop also modifies the stack as they are processed, and we can go back to the slides of this video to make ourselves comfortable with that. During this modification of the stack, we need to track the location of the stack pointer. And after a few push and pops, it really gets so confusing remembering the location of the stack pointer. And you've got to really trust me on that, okay? So what the compiler does after the stack is set up in the Prologue is that the compiler usually declares a space for the local variables. And because the compiler knows at compile time how much space is required, okay? So by subtracting the required number of bytes from our stack pointer, we are actually growing the stack downwards, similar to what we had in the push instruction, except that the push instruction decrements by an amount that has been pushed onto the stack in the line of 4-byte alignment. So the compiler basically subtracts the required number of bytes from the stack. And since we have in our program, we have we need to save the address of the first byte of our string. Okay, so that basically would need 4 bytes, but the compiler actually makes a space, subtracts 16 as a minimum. So as we know that we only need to save 4 bytes because we need to push the address of the first byte of our string. But here we will subtract 32 from the stack pointer. By subtracting 32 from the stack pointer, we are actually growing the stack downwards. Subtract 32, make a room for 8 bytes of data. After declaring a space for our variables, the compiler can now use the move instruction to read and write all those variables from anywhere in the stack and as many times as we require without the need to worry about remembering the location of ESP. Okay. Now we use the leal instruction. Leal instruction load effective address, and we know from our assembly lectures, and we know from our assembly videos what the leal what the leal does. It just calculates for us the effective address, and let's say we want to offset our ESP by 8, and we assign that into EAX, and now we can use the move L instruction to move this value into ESP. But remember, we need the parenthesis to make a memory reference. Okay, we want to move this value into memory location with an offset of 4. And now we can replace the push instruction with our move instruction. Move, and we want to move the message onto the stack. And we already have the stack at location 4. Okay, and if we execute the program, that should give us the same result. And we can see tech instance says hey world. So the move instruction has been used to move our message onto the stack, which gives us an advantage of the flexibility by waiving off dependence on the ESP. And now we can navigate the stack pointer according to where we want to place it directly, right? And that brings us to the last part of the video, that is to take inputs from the user. So now we want to get this from the user who says hey world. That means we want the user to give us a name or a string that will say the hey world for us. Okay, so as we know that in C programming, we place a format specifier. So as we know that in C, so now we want the user to give us this name. We want the user to give us a name or a string that will say the hey world for us. Okay, so as we know that in C programming, we place a format specifier when we want to interact with the user, and the compiler places a format specifier of %s before the hey world message, expecting the user to input a string, right? And we also want to tell the assembler where to look for the string that the user inputs. So we need to specify another memory address. Let's name it input dot ASCII, and we write the string specifier. Okay, so now the assembler knows this address. So this label would be mapped into an address. So the assembler knows where to go and read the string. So this string format specifier would tell the program to jump to the location to get the string, and that location is mapped to an input label where the compiler would go and read this string format specifier. Okay, and we would also require scanf, extern scanf, to scan that string. Okay, this was our instructions used to move our message onto the stack. and print the result. But now before that, we need to specify who says the hey word. So Leal ESP, and similarly we move it to EAX or any register, for example EBX, and we want to move EBX to ESP, but remember with parenthesis and location 4. Move L. We want to move our input message onto the stack. Okay. So after that, we need to call function scanf. Okay. And just one more step, but before that step, let's run our program. And the program has finished successfully. The program finished normally, but we can see here some strange values, okay, because the user hasn't given any inputs yet. So just the last step, we need to specify in the input doc tech instance the string that we want it to say the hey word for us. So this is the input stack. When we call the scanf, when we move this input onto the stack and call the scanf now knows where to look for the string. So the scanf will read the tech instance and display that for us, hopefully. Let's run the program. And hooray, we have the results. Compiled successfully, and tech instance says hey world. You might be wondering why I did not give a space in tech instance. If I give a space in tech instance, it would only print tech says hey world, because the space here is the break statement. This space here signifies the end of the string, right? So combine it again, and we have tech instance says hey world. I hope you understood the program. One more thing that you really need to know is that since our message and our string specifier are not going to change inside our program, we need to declare another section for read data. Okay, so this is the read-only data section, and we compile, and the results are the same, except that the strings are now in a section that is read-only. Okay, I hope now you know how to interact with the user. In the next video, we will play with different data types. We would also see a special data type, that is the array data type. I hope that was cool, and thanks for watching.